Hello everyone, this is my second video note for all the statistics book. This time I changed the setup. I have some previously written notes. I'm going to explain them and add more text and visualization as needed. Okay, so remember our main setup. So this is the way that we look at probability. So we have a set, and that set we call it a sample space, and then it has members. So small omega is a member of the big omega, which is our sample space. And then we can measure each of the members or subset of sample space. Now we have another branch in this diagram, which corresponds to random variables. So random variable is a function. You see that it has an argument from sample space. It maps each outcome, which is a member of the sample space, to real numbers. And another way of writing probability of omega is this. So let's assume that the result of this mapping is alpha. You can inverse that and write it as image of alpha in the sample space, which is just omega. Okay, so this is another way of writing probability of omega. But this is for the time that this mapping is one-to-one. So basically, you go from omega to alpha, and then you can go back from alpha to omega. What if it's not one-to-one? So alpha goes back to a set of omegas, which is like a subset of sample space. So that's also possible. So in that case, probability of x inverse of alpha is probability of that set. So this is image of alpha in the sample space. So basically, you're representing this set in another way using x. Okay, so in short, we write it as probability of x equals alpha. Again, probability of x equals alpha means that the outcome or the output of this random variable function is alpha. We go back and find its image, which is a. And remember that using probability, we only can measure sets. So I'm going to measure this set A. So I cannot measure this point. So this is just another representation of A. Okay. So probability of x equals to alpha is another form of writing probability of A. Nothing more. But as we move forward, we kind of forget about this inverse and going back to the sample space. We're just going to talk about probability of these numbers. Next, we have an example. We flip a coin 5 times, and each member of a sample space is in a string like this. It's a sequence of H and T, head or tail. And we define two mappings for this sequence. For example, the first one is number of heads. So this is number of heads. So for this omega, number of heads is 4. So I have 4 heads in this sequence. Or I can define another mapping for the same sample space. So this one is longest subsequence of all heads. So here again is 4. The value is 4. But if you want to compute probability of x equals 4, you need to think about all the ways that you can have 4 heads. So if you map it back, then you're basically talking about size of this set. So I have 4 heads in a row, and the other possibility is 3 heads and tail and head. You get the idea. So basically we have 5 alternatives. So 5 member for this set. And they have equal probability, and this is a fair coin. That's the probability, and we have 5 of it. So that's the probability of this random variable. So basically, this is a member of a real line. We map it back to sample space, and this is A, and measure the size of that. Okay, so again, this is not one-to-one, so you have multiple omega corresponding to x equals to 4. Or you can make it more complicated. For example, let's think about y of omega belonging to 4 and 5. So what's the probability of that? So instead of thinking about random variables being just one number on the real line, what about thinking about multiple numbers? So again, you need to think about image of these two numbers. So image of 4, so longest subsequence of all h's. So it's going to be either this. So I have 4h in a row and then t, or I have t and then 4 h's. And image of 5, so this is easy, I have only 5 trials. So this is the image. Again, probability of each one of them is this number, and I have 3. Okay, I hope this makes it clear that's how we move between sample space and random variable space. Next, I'm going to talk about distribution functions and probability functions. So the naming is very confusing, but if you think about abbreviation, it's much easier. So we have CDFs, PMFs, and PDFs. So starting with CDF, so it's called cumulative distribution function, or for short, we say distribution function. So distribution functions are specific probabilities. So probability of a random variable being less than some number. So this is a fixed number. This is my random variable. So this is a scalar. And capital F is the representation. So again, this is the argument. So, and this is my function, capital F, and this is the random variable. Okay. So if you look at these two figures, we have a continuous random variable and we have a discrete random variable. Both of them share some properties. So you see that the diagrams saturate at 1. So limit, if you go to right, if x goes to infinity, limit of f of x is 1. If you go to left, which means x goes to minus infinity, limit of f of x is 0. Okay, so this is probability of observing some random variable less than x. So you're saying that if you increase the x, for sure, at some point, your random variable is going to be less than that number. So that's easy to understand. And if you decrease the x, for sure, at some point, the probability of observing some very, very small number, if you go back to minus infinity, is 0. Okay, what else? Another property is that this is a non-decreasing function. So here you have an increasing function, or you have plateau. So again, here you have plateau, and here you have this jump. Okay. Moreover, you have another property which is called being right continuous. So right continuous. So this is a continuous function. So there is no disconnection here. There is no discontinuity here. But here you have discontinuity. But if you think about it, as you move from right to left, you always have a value. So you see that if you decrease the x and move to this point from right, you always have a value. But if you move from left to right, you don't have values here. So we have this property which is called right continuity. Again, if I want to summarize the properties of the CDF that I talked about, I can number them. So this is the first property. CDF is non-decreasing, and also it is right continuous. Okay, moving on to probability functions. So first we have probability mass function. So this is for discrete random variables. So for probability functions, we separate discrete distributions or discrete random variables and continuous random variables. So for discrete random variables, we have PMFs. So this is a function which we use small f to represent, and it's nothing but probability of that random variable at point x. So for example, here is my dice example. So the outcome can be 1, 2, 3, 4, 5, or 6. And the probability of each one of them is equal. It's a fair dice, and it equals 1 over 6. For continuous random variables, it's more complicated. We have probability density function, and probability of each point is 0 for continuous random variables. So probability of x equal a is 0 because, for example, I'm looking at this line segment. Let's say it's from 0 to 100, and this is my a. So probability of hitting exactly this point, whatever random experiment you have, is 0 always, because it's infinitely small if you look at real numbers. So probability of each point is 0. So we can talk about and measure probability of intervals. Okay, I can measure probability of this interval and compare it to this other interval. Okay, so this is why we don't have, like here, we don't have probability of some number, so we have probability of some interval. And probability density function is a function that can help you compute this probability or measure this interval. So this is my probability density function, and it's inside an integral from a to b. And if you think about CDF is going to be probability of minus infinity up to x of this function. So this is my function. So let's talk about diagram. So it's easier to understand if we talk about this diagram. So this is my f of x function, and this is, for example, x. So moving from minus infinity up to x, this integral is going to calculate the area under the curve, and this is my f of x up to x. So this is the visual representation of CDF. So area under the curve of f of x from minus infinity up to x. And from calculus, we know that we have this relationship. So the area under the curve, if you differentiate it, so this is differentiation, you get the curve. And going back to probabilities, so probability of x being between a and b is basically this area. Okay. And another interpretation of f of x is in the limit. So let's assume that we have a plus some small number epsilon. So probability of x being between these two numbers is approximated by f of a. So at this point, so these two are very close, for example, if epsilon is small. So it's like having this rectangle times this value, which is epsilon. So then f of a is approximated by this probability, a scaled version of this probability. So this is another way of thinking about f of x. But you should remember always that f of x is not a probability. It's a scaled version of the probability. So it can go to infinity. So for example, I can have this figure. So this can be my f of x. So in all of the other diagrams, you see that 1 is the limit. So you cannot pass 1. But here you can go to very large numbers, because this is f of a at each point is some scaled version of probability, and if epsilon is small enough, f of a can be very large. Okay, so just remember that f of x is not a probability. Moving on to next part, we have some important discrete random variables. I've put together all of them in a single page, and I'm going to explain them one by one. So this is a general way of writing the fact that distribution of x is f, and f can be any of these distributions, and it's going to have some parameters. So let's start with the simplest one, point mass. So we write x has point mass distribution at A, and we mean that the only possible outcome of this random variable is A. So this means basically that probability of x equals A is 1 and 0 in every other place. So this is the way that we write probability distribution of random variables. So this is the name of the probability distribution, and this is a parameter. Next, we have discrete uniform random variable. So we have x distributed as discrete uniform, and these are possible outcomes, possible values for a random variable. So here we have 4 possible outcomes, and the probability of each one of them is equal, and probability of x equals any of those outcomes is equal to 1 divided by number of them, because it needs to sum up to 1. So another important random variable is Bernoulli. So this is the coin flip random variable. So the probability of head, for example, is P, and this is my head. This represents my tail. So probability of x equal 1 is P, and probability of x equals 0 is 1 minus P. And a very handy way of writing this compactly is this. So probability of my random variable being 1, so x equals 1, it's going to make this 0 and this 1, and it gives me the correct answer, which is P. And if x is 0, this is going to be 1, this is going to be 0, and it gives me the correct answer, which is 1 minus P. Okay, so basically this is a compact way of writing this function. Next we have binomial distribution. So this corresponds to probability of x success in n Bernoulli experiment. So I flip the coin n times, and the probability of success in each one is P. And what's the probability of getting x success? So here is an example. So I have this sequence. I flip the coin 5 times, so this is one parameter, how many times you flip the coin. And this is a fair coin. The probability of success, which is another parameter, is half. And success is defined by having h as the result. And the corresponding random variable is 3, because I've observed 3 h's. But in reality, if you compute the image of 3, you get so many other random variables, so many other events. And you need to sum up all of those events. So in reality, you get 5 choose 3 events, and then probability of each one of them is half to the power of 3. So you need 3 success, and you need 2 failures. So this is how we come up with this formula. Okay, and we write it as x distributed as binomial with 2 parameters n and p. N is number of trials, and p is the probability of success. So I forgot to write it for Bernoulli. So x is distributed as Bernoulli and with probability p, which is the only parameter that we have. Next, we have geometric random variable. It's similar to binomial, so it's a sequence of Bernoulli trials, but you continue the Bernoulli trial until you get 1 success. So how many times you need to flip the coin until you get a head? So here, for example, the value is 3. And this is interesting because this is a one-to-one mapping. So each string maps to exactly one random variable because after having a head as an outcome, you stop. So, for example, this corresponds to 2, so forth. So you see that for any x, you need x minus 1 failure and then 1 success. Okay? We say that x is geometrically distributed with parameter p, which is a success probability. So the final random variable is Poisson random variable. We use it to model counts of rare events. Because of that, you're looking at positive integers. And I'm writing this symbol, which means proportional to. So this is the form of the Poisson distribution. To be more specific, this is the exact value. So again, this is the part that depends on x. So this is some function of x, and this part is not a function of x. And this is just for normalization, which means it ensures that summing all of the x's is going to be 1. Okay. And lambda is the average rate. So you can show that on average, you can expect lambda events, let's say per second. And another fact is that if you have 2 independent Poisson random variables, the sum of them is also a Poisson random variable with a rate which is the summation of 2 rates. So for example, let's say I have a Poisson random variable representing how many female customer I'm going to have in an hour, and another random variable representing how many male customer I'm going to have in an hour. And then you can imagine that because those two are independent and with separate rates, and rates are different because I'm selling something which is more appealing to female or male. But finally, what I get as the total number of customers is summation of those 2 random variables. Those are independent with different rates, and it's going to be another Poisson random variable with a higher rate. Next, I'm going to talk about some important continuous random variables, starting with uniform. Uniform is the simplest one. You have uniform distribution. X is uniform between A and B. And because it needs to integrate to 1, this area, you need to have probability of 1 over B minus A for the whole area. You can remember that this is my f of x for x. Another important distribution in statistic is the normal distribution. So this is the formula for normal distribution. It seems complicated, but you can focus on the parameters of this distribution. You have mu and you have sigma. And if you plot this function, you're going to get a unimodal distribution. So you have only one hill, you have only one bump, and that mode, that highest point, happen at mu. So when x equals mu, you have this. And the spread of this distribution is determined, the spread of this function is determined by sigma. So if sigma is large, it's going to be a wider function. Okay? And the crucial part of the form is this. So x minus mu sigma squared. So this is what you have over here. And we have a couple of properties for this distribution. So if x is normally distributed with these 2 parameters, mean mu, so we call mu the mean, and sigma squared variance or sigma as a standard deviation. So if these are your two parameters, if you make another random variable, which is this, x minus mu divided by sigma, so basically replacing this with z, for example, then this is again a normal distribution with mean 0 and sigma equals to 1. If you think about it, the form of f of z is like this. So f of z is proportional to e to the minus half of z squared. Finally, we have a specific name for CDF of standard normal distribution. So we call this standard normal distribution, which means that mean is 0, standard deviation is 1. We call CDF of this phi of x. And we have this nice theorem which tells us that for any normally distributed random variable, so it's normal, mu, and sigma squared, you can compute probability of x being between a and b as this. So you can use the phi function, which corresponds to the standard normal distribution, to compute this probability for any normally distributed. Okay, next we have the gamma distribution. So if you look closely, we have this part of the formula for gamma distribution, which has x in it. So x to some power, and then e to the power of x minus x times some number. And then we have another part of this distribution which doesn't have any x in it. And we have this weird gamma function. I'm not going to talk about the gamma function. You can think about this term just as a normalization term. This makes the distribution to integrate to 1. Okay. And so gamma distribution is a general distribution. We have a special case of gamma distribution. So the first one is exponential. So if you look closely, you see that if you set alpha equals to 0 for in the gamma distribution function, you get this formula. And this is just an exponential function normalized. So if you set the value of x to 0, and remember that this is only defined for positive x's. So if you set the value of x to 0, you get 1 over beta, and that's your first point in the distribution. And then it decreases as you increase the x. And remember that beta can only be positive. And that's the case also for the gamma distribution. I forgot to mention that beta is positive. Also, alpha is positive. Okay, and exponential distribution is used to model time between rare events. So if you remember, we had Poisson distribution to model number of rare events in an interval. And you can show that if you have Poisson distribution for number of events, the waiting time, the time between events, is exponentially distributed. So that's an interesting property. Okay, enough for exponential distribution. Let's move on to the chi-square distribution. Again, chi-square distribution is a special case of gamma distribution for beta equals to 2 and alpha equals to p over 2. So beta is fixed, so chi-square distribution is only determined by alpha or p here. So we usually write it as chi-squared p. It is called the degree of freedom of the chi-square distribution. Another point that I forgot to mention is that you see that you can write exponential distribution as this, but we insist on 1 over beta formulation because beta is the average, is the expectation of x. So we're going to talk about expectation, but let's think about it as an average of the distribution. Because of that, we prefer the 1 over beta formulation. But in general, whenever you have e to the power of x only in the distribution, you can think about it as an exponential. Next, we have the beta distribution. This is my favorite distribution. It's defined between 0 and 1, and its kernel is x times 1 minus x, and they have some power. So again, we're only worried about the part which is a function of x, and we don't worry about constants here, so we have this proportional sign over here. It can take many shapes in the 0 to 1 interval, but it can only have one mode, like one bump here, or in an extreme case, it can have two modes, one at 0 and the other one at 1. It can also be a uniform distribution. So basically, beta distribution is a generalization of the uniform distribution. And it's a very useful distribution to model things that are between 0 and 1, for example, probabilities. So you can model probabilities of, for example, Bernoulli as a beta random variable. At the end, I want to briefly talk about kernel of a distribution. We have seen it several times during our discussion of important distributions, but it's worth emphasizing on. If you think about it, each probability function has two parts. So it has a part which is a function of x, and you can take out or factor out a part which is not a function of x. And because we have this relation for this equation for a probability function, it should integrate to 1. If you write it and plug in that factorization, h times g, you can take out h because it doesn't depend on x, and then h is just 1 over this integral. Okay, so for any function x that this integral exists and is finite, so for all g such that this integral is finite and also is not 0, you can find this h and use it as a normalizer. So this is the normalization that we need. We need the f to integrate to 1. Because of this decomposition, it's okay to only worry about g of x, because usually you can integrate that g of x and find the corresponding h. So we call this g the kernel of the, we call this g the kernel of the probability function, and this h is just normalization constant. Okay, let's move on to bivariate distribution. So we have been talking about f of x. This is just one variable. Now we want to talk about two random variables, f of x and y. So remember the sequence that we had. We have sets, which are outcomes, subset of sample spaces, and we map them to real numbers using random variables, and then we measure the corresponding sets to the random variables. Now, instead of having one function, so we have omega or a, or let's say omega, we map it using function x. We can also map the same thing using y. And if you think about this as being alpha, this being beta, then the corresponding, going back to the sample space, the corresponding events are, let's say a, which is x image of alpha, and image of beta, which is b, for example. And then we compute the probabilities of alpha as being probability of actually a, and probability of beta as being probability of set b. So you can think about these two mappings, these two random variables separately, and that's fine. So we have already covered these, but you can think about them jointly. Now the question is, what's the probability of x being alpha and y being beta? Why? Because these two go back to the sampler space. And that's basically asking, what's the probability of A intersect with B. So I go back to the sample space. Every event that generates alpha as my random variable, I represent it with A. Same for Y, I represent it with B. I'm looking at the outcomes that are at the intersection of these two events. So in general, you don't need to have only alpha and beta, just two numbers. You can have arbitrary sets. So here, X and Y belong to some area A. So you can think about it as a 2D thing. So I have X and Y, and this is my A. So they're not just one point. So previously we were thinking about it as alpha and beta, but now they can be an area. Okay. So for each point in this area, I go back and find the corresponding sample space, find the corresponding part of the sample space. So let's call it calligraphic A, for example, and then compute that probability. And this is the mathematical way of writing it. I'm looking at any events for which, if you map that event by X and map that event by Y, you get a point in this area. Now some example. The simplest example is two binary random variables. So we call this joint mass function. So I have two binary random variables. So X can be 0 or 1. Y can be 0 or 1. Let's assume that I have, for example, the coin flip experiment. I flip the coin twice, and these are independent. And this is my head, this is my tail. And probability of observing any combination 0, 0, 0, 1 is 1/4. And I'm going to write on the margin of this table the probability of observing, for example, Y as T. So I sum up these two and write it as half, because whatever I get as a result of my first flip is not going to change the probability of the second flip. So it's half, and this one is half, and this is half, this is half. So we call this joint mass function. So how X and Y covary. So here, for example, f of 0 and z, and 0 is 1/4. Next, we have the joint distribution function. So this is a 3D figure. I have X and Y, and I'm interested in probability of X, Y point belonging to set A, so here. And this is my density function. So basically, I need to take the integral of the density function. This is the two-dimensional integral in this area. So basically, I'm interested in the area under this curve, and this is going to be my probability. Again, you can think about joint mass function also in 3D. So this is my 0, 1, 1, and this is x-axis, this is y-axis. And I have 4 points, and each one of them, we have a bar, and the height of this bar is 1/4. Okay, so for discrete distributions which have joint mass function, you can also draw these 3D plots. Next, I'm going to talk about marginal distributions. So we sum over or integrate out one of the random variables. So I have two random variables here, for example. So this is my joint distribution. And then I sum over y. So for all values of y, I'm going to compute this and eliminate the y. So this is going to be only a function of x, and this is exactly probability distribution of x. So for the discrete distributions, we talked about marginals. So for example, here, if I want to, this is my x, this is my y. If I want to eliminate x, I'm going to sum over here. And this is, for example, f of y for 0. And if I want to eliminate y, I'm going to sum in this direction. And this is my f of x for 1. Okay. And this is called marginalization because we are writing in the margin. This figure is already complicated, but let's change the color. So we write in the margins the summation. So this is called marginalization. And we have the same concept for continuous distribution. So this is for discrete distribution. This is for continuous distribution. So you can think about marginalization in 3D for the continuous distribution too. So here, for example, let's assume I'm looking at x equals to 5. So f of x for 5 is just this integral. So fix x, which is 5, y, and then dy. So think about a plane at 5 that you pass through this 3D f, and you have this slice of the distribution. So this goes to infinity, this goes to infinity. So because of that, you have this slice of the distribution. It's just like a 1D figure. And then the area under that is what you compute over here. And then you compute that area, and that's going to be your f of x at 5. And then for each point, you do the same thing, and you finally get your marginal distribution. Next, we have independent random variable. So for that, we need 2 random variables first to start with. So random variable x belongs to some set in the R. So for example, here is set A. So it's just an interval in R. And B belongs to another set. And if probability of joint event, so probability of x being in A and B and y being in B, so basically probability of this rectangle. If this probability can be factorized as probability of each one of them, then we say that x and y are 2 independent random variables. And we have a theorem saying that if you can factorize the joint probability function, probability mass function or probability distribution function, to 2 functions which separate x, so all of the x's in this function is here, and y, then x and y are independent. Okay, so this is my f of x, and this is my f of y, and the area under this curve is basically the probability of y being in B, and it maps to some events in the sample space, and probability of x being in A is the area under this curve, and this also maps to something in the sample space. Again, we shouldn't emphasize on the sample space a lot because it doesn't matter anymore as we move forward. But what we say here is that the area under these 2 curves, the yellow one and the green one, if you multiply those 2 numbers, you get the area under the 3D curve. So the one that I haven't depicted here. So for any A and B, if you compute those two areas, multiply their value, you get the value for the area under the 3D curve. And that's very interesting property. And you can show that because this holds for all A and B, it's going to be very hard to check, but you can show that that's exactly equivalent to factorizing the algebraic form of the joint distribution. So if you can factorize this, you have the independence. Next, we have conditional independence. So it's very similar to conditional independence in the sampler space. So if you remember, A is an event, it's independent of B if. Next, we have conditional distribution. It's very similar to what we had for sampler space. So probability of event A given B was probability of their intersection divided by probability of B. Here we have the same form. Probability of X given Y is their joint probability divided by the marginal probability of Y. And in discrete case, and that's the same for both discrete and continuous case. But in discrete case, this has exact probability meaning. So we are comparing two measures, two probabilities, so one in the denominator, one in the denominator. But for the continuous distribution, again, because probability of each point is 0, we cannot have this. We can have probability of some area. So probability of X belonging to some area given Y is something, is the integral of the joint distribution computed in this area. Okay, so that's the difference. So by definition, both of them are the same. So we have this ratio for both of them as a definition of conditional probability, but conditional distribution. But conditional probability has different form for discrete and continuous random variables. Next, I'm going to talk about multivariate distributions and IID samples. So we talked about single variable, and then we talked about bivariate distributions. Now we have multiple variables. So we have x1 through xn, and we can talk about their joint mass or joint probability distribution. And because we want to unify discrete and continuous distribution, we drop this and we just say joint distribution. So joint distribution is basically f of these. And again, the notation is confusing. Remember that for P, we call it probability or probability measure. And for CDF, we call it quantitative distribution function. So we call this distribution function, and we call this probability distribution function or probability mass function, or in general probability function. But now we call this joint distribution. Okay, so here it seems that distribution means CDF, but here when we say joint distribution, we mean PDF. So it's a little bit confusing. Just focus on the symbols. So it's much easier to understand the meaning of the math if you focus on the symbol. And so F is for PDF, and small f is for PDF, and capital F is for CDFs. Next, we defined a generalized version of independence. So these random variables are independent, x1 through xn, if you can factorize their probability to the product of individual events. If you can factorize their joint probability to product of their individual probability. And again, you can check it. So there's a theorem showing that if you can factorize the joint distribution, for sure you can factorize the probabilities. So because of that, you only need to check this, to check independence. Finally, we say that random variables x1 through xn are IID, or independent and identically distributed when they are independent, and then they have the same distribution. Okay, and usually it's the case that we have some underlying process. For example, we have the coin flip experiment, and we repeat it n times. So flip the coin once, and you have one Bernoulli random variable. Flip the coin twice, the second one, so forth. And these are independent because the result do not affect on each other, and they come from the same distribution. You are flipping the same coin. It's just some Bernoulli with the same parameter p, and because of that we call this identically distributed. Next we have transformation of random variables. So this is a complicated topic if you want to go into the details, and the book does not do that. So the general way of thinking about it is that I have xn random variables, and I have a function applying to them to get another random variable. So function of something random is also random, so y is also a random variable. You can think about the CDF of y, so probability of y being smaller than some number. And if you replace the y definition with x using this g function, you get this. And then you go back and find the image of any point in the y space that is less than this number. So all of the n-dimensional points that generate some value less than y. Okay, and then you compute probability of those. So basically, you need to go back to the n-dimensional space and compute the probability there, because that's the space for which you have, for example, probability of x1 or distribution function of x1, so forth. So because of that, you should find the image of all of the y's in that space and compute their probability. Okay, so basically the assumption is that you have the joint probability distribution. So I have the joint probability distribution of x1 through xn, and I want to use that to compute the probability distribution of y. Okay, and if you go back and find that set A, and then integrate over that set A, this function, integrate this function over that set A, you get the CDF of y. And so this seems very complicated. It's a general way of doing this, and it's not easy in general. But if G is invertible, everything gets much easier, because I know that, for example, let's assume that I have only one variable. So y is equal to g of x, then f of y is probability of gx less than equal y, and then you take the inverse. So it's a one-to-one mapping. It's going to be x less than g inverse of y. And because you know CDF or PDF of x, you can compute this. So this is exactly f of x for g minus 1 of y. Okay, so if G is invertible, everything is easy. Otherwise, it's hard. You should compute this manually for every problem. Okay, finally, some example of multivariate distributions. The most important one in the discrete case is multinomial. So multinomial, so you can think about multinomial distribution as follows. So you have this urn, you have some balls in it, and they have different colors, and you have different number of them. So you have 1 pink, 5 white, and 4 red, so forth. And you have 16 of them. So probability of taking out each color is the number of that color divided by 16. So that's my probability vector for each color. So for pink, for example, probability is 1 over 16. And for blue, is 2 over 16, so forth. And you sample with replacement n times. So you take out various balls n times, and this is with replacement, so you can do it infinitely many times. So you do it, for example, 8 times here. And the question is, what's the probability of getting, so my x is a vector, getting 2 pink, 1 white, 2 red, 3 blue, 3 green, and 0 blue. So that's the probability that I'm interested in. So probability of getting this sequence exactly is this. So let's say the first 2 trial I get 2 pings, it's 1 over 16 to the power of 2, so forth. But the order of them is not important. So you're going to compute how many different order you can have that generates the same vector. So that's how many. So that's 8 choose these many numbers. And in general, this is the formula for it. So the formula for multinomial distribution is like this. So you have your probability vector P, which is n-dimensional, P1 through Pn. And the question is how many of different colors after n sample you have. And notation-wise, now we have 2 parameters. So we have n, number of trials, and P is the probability vector. And if you compare it with binomial, you see that it's the same. So binomial has 2 parameters. So remember, binomial is you flip a coin n times, and the probability of success is P. So probability of success here is scalar. And the formula is kind of similar. So this is your P1 to the power of x, and this is your P2 to the power of x2. Okay, but you have this relationship between P1 and P2 because they need to sum up to 1, and you have x1 plus x2 equals x. So because of that, you can simplify it and write it this way. So basically, multinomial is a generalization of binomial distribution. Okay, finally, the most important multivariate continuous distribution, which is a normal distribution. So remember the form for the one-dimensional normal distribution. It was, so the kernel was this x minus mu sigma to the power of 2. Okay. Now it's more complicated. So instead of just variance, you have the covariance matrix here, and you have inverse of this. So variance here is in the denominator. Because of that, you have inverse over here. And instead of this quadratic form, like x minus mu to the power of 2, you have a vector form of that. So x minus mu, both of them are vectors, and transpose times this matrix times x minus mu. And also you have the determinant of your covariance matrix here. Some facts about normal distribution, multivariate normal distribution. So if you have n standard normal distribution, so mean 0, standard deviation 1, and they are independent, so they're coming from the same distribution, they're independent, so they are IID, then their joint distribution is also normal. And it's like this. So basically, the covariance matrix is the identity matrix, and this is the definition of identity matrix. Diagonal elements are 1, off-diagonal elements are 0. So because of that, this form reduces to this. Next, if x has this multivariate normal distribution with mean mu and covariance matrix sigma, then sigma to the power of minus half times x minus mu has this multivariate standard normal distribution. So mean is 0, and covariance is I, which is identity. So basically, if you do this transformation, you kind of make the resulted random variables independent, because we know that that's the form, and you can factorize this form. So because of that, that's kind of making dimension of x independent from each other. So basically, you're transforming your vector x to some vector y using this transformation, and now you can say that y1 is independent of y2, so forth. But here, that wasn't the case. So we are not sure that if x1 and x2 are independent or not. But if you do this transformation, you make all of the elements of this y vector independent. Finally, if you divide x to 2 components, so XA and XB, so basically 2 blocks for this random variable, and use the same index to divide mu to 2 blocks, also the covariance matrix to 4 blocks. You have these facts about each block. So XA is also normally distributed, so the part of that vector which you separated is normally distributed. You can imagine, because it's symmetric, XB is also normally distributed with mu B as its mean and sigma BB as its covariance matrix. Also, interestingly, XB given XA, so one part of that vector given the other part, is normally distributed. And the formula is very complicated, but you can think about it as updated version of the above form. So here I have mu B and sigma BB. So here I have mu B plus something and sigma BB minus something. So basically you update the mu and covariance matrix. So that's in general good to know, that if you have a vector which is jointly normal, so we call this jointly normal or multivariate normal, and if you divide it to 2 parts, each part given the other one is also normally distributed. And next, if you multiply your vector by another vector, you get some random number y, and that is also normally distributed. So this is the mean, this is just a scalar, and this is the variance. Okay. And finally, the quadratic form x minus mu transpose. So this is, remember, the exponent here. Here is the exponent. The distribution of that quantity is chi squared with k degree of freedom, if this is a k-dimensional vector. So if you have x1 through xk, and you form this random variable, which is a scalar, so this is a scalar, its distribution is chi squared with k degree of freedom. Yeah, so that's the summary of chapter 2. Please give me your feedback in the comments or on Twitter or on Discord, and help me to improve the quality of these summaries. I'm going to also put more details of each part on my Rome graph. Thanks.